Standing in the Qutub Minar complex in Delhi is a massive iron pillar that has been exposed to the brutal Indian sun and torrential monsoons for over 1,600 years. Yet, if you walk up to it today, you won't find a single flake of rust. Half a world away, medieval crusaders returned from the Middle East terrified of Damascus swords. These blades, forged from Indian wood steel, were renowned for slicing through chainmail as easily as silk. And deep inside the Ajanta caves, murals painted 15 centuries ago still radiate brilliant blues, reds, and yellows that refuse to fade. For a long time, it was easy to dismiss these anomalies as historical accidents, or perhaps the result of mythological exaggeration. But a 2026 metallurgical analysis proved otherwise. When material scientists examined fragments of 11th century Indian wood steel, they found microscopic carbon nanotubes structurally woven straight into the metal's molecular lattice. You don't get nanotechnology by accident. These artifacts are the surviving evidence of a highly organized technical system of chemistry and metallurgy, one that relied on specific geometric furnace designs and standardized ratios pioneered in the Indian subcontinent. Take the extraction of zinc. Zinc has a uniquely low boiling point. As you can see in this standard furnace design, if you heat zinc ore from below, the metal turns into a gas and floats right out the chimney before you can collect a single drop. To solve this, Indian metallurgists at Zawar invented a specific physical workaround: downward distillation. They packed a mixture of roasted zinc ore and charcoal into specialized brinjal-shaped clay retorts and sealed them completely shut. By applying intense heat to the top of the retort, the volatile zinc vapors were forced to travel downward. They passed through a layer of perforated bricks and instantly condensed back into solid liquid drops as they hit a pot of cold water waiting at the bottom. By deliberately manipulating the states of matter, from solid to gas, back to liquid, these artisans were solving complex chemical engineering problems centuries before the Industrial Revolution. That same mastery over extreme heat allowed them to forge the ultimate ancient alloy, high-carbon Wootz steel. Their method, known as the crucible process, required sealing specific raw materials inside a clay vessel. They packed it with chunks of iron, charcoal, pieces of glass, and select plant catalysts. Inside the blazing furnace, a violent thermomechanical reaction took place. As the materials melted, the solid iron absorbed pure carbon from the organic plant matter. This specific heating and cooling cycle forced the carbon to bond within the iron's internal structure. The resulting lattice gave the steel two contradictory traits: extreme surface hardness and the flexibility to bend without snapping. This recipe was so specific that decades later, elite European scientists, including Michael Faraday, tried to duplicate it in their modern labs and failed completely. The traditional Indian forge operated as an advanced chemistry lab, where blacksmiths were engineering materials near the nanoscale. But the metallurgists applied these exact same principles beyond weapons and architecture. They brought them into the Rasashala, the ancient Indian alchemical laboratory dedicated to health. Here, the goal was Rasayana, an intensive medical discipline focused on cellular rejuvenation, boosting immunity, and pushing the limits of human longevity. To achieve this, practitioners took on a dangerous challenge. They aimed to purify highly toxic heavy metals, specifically mercury, known as parad, so it could be safely ingested. They developed an exhaustive 8-step purification procedure called the Asht Sanskar. Using specialized apparatuses known as jantrans, they meticulously steamed, rubbed, and sublimated the raw mercury to strip away its toxic impurities. Once the mercury was stabilized, they systematically bonded it with the extracted juices of medicinal plants to create health-boosting medicinal compounds. This sequence of steaming and sublimation was an application of the same distillation principles used to refine industrial zinc. By managing these specific chemical reactions, they were taking the exact techniques of the forge and applying them to the chemistry of human biology. And it is this precise chemistry that explains the artifacts we see today. The iron pillar of Delhi doesn't rust because its creators engineered a composite protective film of iron hydrogen phosphate onto its surface. Damascus blades held their edge because of carbon molecular manipulation. And the Ajanta murals still glow because they are coated in chemically stabilized mineral and plant extracts. For a very long time, Western scholars read ancient Indian texts like the Arthashastra and categorized them strictly as philosophical, spiritual, or administrative writing. But modern material science tells a different story. These texts are precise engineering and chemistry manuals, and they secure India's legacy as a foundational hub of global scientific discovery.